Okay guys, so today we're going to talk about section 3-7, which is the chain rule. Okay, so the chain rule is extremely important because it allows us to differentiate, so take the derivative, so to differentiate a composite function. So just to make sure we're on the same page, let's take a little walk down memory lane and think back to Algebra 2. So composite functions all have the form f of g of x. Okay, so this is a composite function. Okay, so now this is a g, sorry, it's kind of ugly, f of g of x. So my composite function is made up of two functions, an inside function and an outside function. So in this situation, whatever's inside is the inside function. So g of x is your inside function. Okay, and f of x is your outside function. So when we think about taking a derivative of a composite function, we need to keep in mind the derivative of both our inside function and our outside function. Okay, so the easiest way to do this is to just jump right in and look at an example. So let's go ahead and look at the same example they give you in your book. Okay, so example 1. So we're going to look at the function f of x is equal to sine of x squared. Okay, and we need to find f prime of x. Okay, that's our goal. So my function that I'm given, sine of x squared, is made up of two functions, a sine function and an x squared function. So the first step is to figure out what is our inside function. So in this case, it's fairly easy to tell because x squared is literally inside my parentheses. You can also think of your inside function as your independent function, okay? My sine function depends on the value of x squared. So that's where I'm going to start. So I'm going to graph x squared just so we can take a closer look at what's happening there. So I don't know why. So x squared looks something like this. It's a parabola. You guys should all know that. Pretend it's nice and pretty. So your inside function, some guy decided that your inside function should always be referred to as u. Okay, so let's add that in. Your inside function is always u. So this graph is my graph of u, which in this case is x squared. Okay, now if I take the derivative at some point here on my graph, so let's whatever that point is, I'm going to take my derivative. So I need to find the slope of my tangent line, which looks like that. And I'm no longer looking at y, because instead of calling it y, I'm calling it u. So instead of writing dy dx, because I don't have a y, I'm going to write du dx, because my function is dependent, or I'm sorry, my function uses the variable u, not y. So I can say that du dx, okay, of my function, so of x squared, would be the same as, well, it wouldn't be the same. It is 2x, right, if I use my shortcut rule, okay? So when I just look at my inside function, my derivative is 2x. Now let's look at my outside function, so my sine function. So if I just start graphing sine, it'll look something like this. And since I'm calling x squared u, instead of writing sine of x squared, I'm just going to write sine of u, because I'm just going to sub it in. So this is my sine of u, okay? Now again, if I'm taking the slope at the same point, let's do it in different colors so you can see it. I'm taking the slope right there. So this is my slope. So now I'm back to setting my function is now back to being equal to y, right? It's f of x here, okay? Just change my x value. So in this situation, we would say that y equals sine of u. So when I take my derivative here, right here, I'm going to use the notation dy du, because u is my inside variable. That's the derivative, that's the variable I'm taking the derivative with respect to, okay? I'm taking the derivative of y with respect to the derivative of u, okay? So when I do that, I'd write it out like this. dy over du of sine of x, or I'm sorry, sine of u. So then I need to figure out what sine of u is, or the derivative of sine of u. And hopefully you have your pink and blue chart handy, and you know that the derivative of u is just the cosine of u. Great. So now we found our inside function derivative is 2x. Our outside function, the derivative is cosine of u. I know that this notation can be a little confusing, but the more you do it, the easier it'll get, I promise, okay? So now I need to figure out what my graph of my composite figure looks like. So you don't always have to draw the graph. I happen to know what the graph of sine of x squared looks like. Well, I put in my calculator, so I know what it looks like. But it looks something like this. Okay? So, and again, I'm going to look at the derivative at this point, right here. So the same point I've been following along this whole time. It doesn't need to be right there. I could have moved my derivative anywhere around, but I'm just trying to be consistent for you guys. So now I'm back to saying that y is equal to sine of x squared, okay? Remember, because I started by taking the derivative of x squared, then sine of u. Now I'm taking the derivative of my entire composite function, which is the original function I'm given. So this derivative then is dy over dx. Now, I have no idea what dy dx is. Okay, I can't solve that. But I can use what I know about my fractions, okay, and my derivative notation I've used here and here to see if I can figure out what dy dx is, okay? So I know that my derivative here I wrote as du dx, okay? My derivative for sine of u I wrote as dy du, okay? And I know that the derivative of my composite function needs to be dy dx. So think about it for a second. What can I do to these two fractions to get them to only be this one? Well, hopefully you noticed that these du's will cancel out, which will leave me with dy dx. So in order to figure out my derivative of dy dx, I just need to plug in my derivative of du dx and dy du, okay? So that will give me 2x times the cosine of u, okay? Because that's my 2x is my derivative for du dx, cosine u is my derivative of dy du. Now, I don't want a u in my answer, so my last step then is going to be to replace u with what I originally set it equal to, which is x squared. Okay, so this is the derivative of my composite function. Now, this work that we just did is a lot of work. I get that. And you don't have to do it every time. In fact, after this example, you never have to do it again. I just want you to be aware of why the chain rule works, okay? And it works because you're just taking the derivative of my inside function, my outside function, and you're essentially just multiplying them together to get your final function. That's all you're doing. In fact, that is the definition of the chain rule. So the chain rule says, if I just move this up, so the chain rule, right? This is why we're doing this whole thing, is so we can get to this fancy, fancy rule, okay? So the chain rule. Okay? So the chain rule says that if you have a composite function, okay, and they're both functions are differentiable, okay? You can't differentiate a function that there's no derivative of. But if you have a composite function, the derivative, so dy dx, is going to equal dy over du times du dx, okay? And then we can say where y is a differentiable function of u and u is a differentiable function of x, okay? If we think back to our composite figure notation that we did all the way up here at the top, we can also use this sort of notation to denote the chain rule. And if we did it that way, we would say that if f of x is equal to g of h of x, then f prime of x is equal to g prime of h of x times h prime of x, okay? Notice that with this notation, g of x is now my outside function, h of x is now my inside function. So let's do one more example just really to solidify the idea of the chain rule, and we will work on this a whole bunch more later this week in class. So example 2. Okay, I need you to find d dx of x to the 6th plus 2 cubed. Okay, so the first thing I need to do is figure out what this is a 6, by the way. So the first thing I need to do is to figure out what my inside function is, okay? So again, the situation's pretty obvious because my inside function is literally inside parentheses. So in this situation, I would say that u is equal to x to the 6th plus 2. Okay, also, from our definition of the chain rule, we know that dy dx is going to equal dy du times du dx. So we need to find these two things. We need to find dy du and du dx. So I don't care which one you want to find first, it doesn't matter. So in order to find dy du, I need to take my u value, my u, and plug it into my original function. So that's going to give me dy du of u cubed, okay? Which I know when I differentiate is going to get me to 3u squared using my shortcuts, okay? That's totally fine. So just so I can keep track of stuff, I'm going to write that right here underneath my formula, du squared. Okay, now I'm not done because I also need to find du dx, okay? So this part of my chain rule, okay? So to find du dx, that means I need to differentiate this function, okay? So du dx, and I need to differentiate x to the 6th plus 2, which is going to give me 6x to the 5th, okay? And again, based on my chain rule definition, I need to plug in this value here, okay? So that's what I'm going to do. I'm just going to rewrite it there. 6x to the 5th. Now, I'm almost done, but I have one last step. My answer cannot have this u in it, okay? That is not good. That's a no-go, okay? Bad news bears. I don't need a u. Don't add extra things. So my final step then is to replace this u with what I set u originally equal to be, okay? So that would give me 3 times my original value of u, which is x to the 6th plus 2, times 6x to the 5th, okay? And that is your final answer. Make sure you wrote everything down. All of these notes need to be complete. I will check them tomorrow in class, okay? If you did not take notes, go back and write everything down now. If you have any questions about this, write them down. You will forget them before tomorrow in class. Write down your questions, write down your notes, and I will see you in class on Friday.